This is video clip 4 in the lecture on the value of accuracy. Here, we look at the value of accuracy in battery current measurement. To assess accuracy, we first need clarity on how we use the battery current measurement. The current measurement serves as an input to state estimation algorithms and fault detection. For fault detection, we tend to have firm specs. Either the sensor is accurate enough or it isn't. For state of charge estimation, the situation is more complicated. Let's take a look. Recall how battery current information is used. Voltage provides the ground truth measurement, and the battery current measurement is integrated for SOC estimation while current is flowing. For LFP cells, the curve is very flat through most of the operating range. State of charge estimation relies heavily on the battery current measurement, much more so than for cells with a steeper OCV-SOC slope. In both cases, the cell voltage determines when we stop charging and stop discharging, and thus affects actual available capacity. The battery current measurement affects our SOC estimation. It affects what the system displays to the user or system controller, which may differ from the actual available capacity. Lastly, observe how the importance of battery current measurement accuracy is greater with LFP cells than with NMC or similar cells due to the steepness of the OCV-SOC slope. Let's say that again. We stop, charge, and discharge based on voltage, and thus the cell voltage measurement affects actual available capacity. Battery current measurement accuracy affects state of charge estimation error, or equivalently, the error between the estimated and actual residual capacities. The system may be at one state of charge, but if the SOC estimate is inaccurate, we might tell the user or system controller something different. The difference is our estimation error. How much this error matters depends on the application. In a car, the SOC estimate is important because it directly leads to range estimate. Overestimating the available range may leave a driver stranded, since they may embark on a trip that they cannot complete. Also, since the estimation error is very visible to the user, underestimating the range or erratic estimates may irritate customers. For home solar storage, the impact is moderate. In a grid-connected system where solar panels provide supplemental energy, the actual capacity matters more than the estimate. The solar panels will charge the battery until it's full, the system will discharge the battery until it's empty, and then the system will use power from the grid. The impact of switching between grid and battery a little earlier or later than estimated is more about looks than function. An inaccurate estimate may look inelegant to the subset of customers who monitor their systems closely, who may be annoyed by poor estimation in an expensive system. For an electric assist bicycle, the functional impact of estimation error is limited, since the user can pedal the bicycle to get to their destination. The user constitutes a backup energy source. Let's talk through what it might take to analyze the value rigorously to find a dollars per milliamp target. We can build a system model and run a sensitivity analysis, wherein we apply some error to the current measurement and observe the consequent error in the SOC estimate. To put that in terms of dollars, we must tie that estimation error to something with value. Perhaps the average cost to tow a stranded car is $300. Or perhaps the assigned value is not entirely rigorous. For example, we might assume that every mile spent pedaling carries some cost, and a company executive might assign a dollar amount to user annoyance. Not every vehicle system will suffer, so we need to estimate the frequency of occurrence, ideally using field data such as drive profiles. From this, we can calculate the average cost per vehicle, including both the vehicles that suffer the problem and vehicles that do not. We can then repeat this analysis with different magnitudes of current measurement error to characterize the relationship between current error and cost to get that dollars per milliamp relationship. Unfortunately, sensitivity analysis is tough to do in early design when the hardware, including the current sensors, doesn't yet exist. the software and algorithms underlying state estimation are rarely ready before the hardware, and field data become available after the product is in production. In other words, this analysis often isn't possible when the current sensing is being defined and designed. In practice, current accuracy may be an example where the traditional approach is best, wherein a company executive or product manager or system architect sets a performance target based on their intuition or past experience, and the engineer designs to this intuitively chosen target. The key takeaways in this section are that current sensing matters most for SOC estimation, less than for actual capacity. Assigning value to an estimate is tricky, and so an intuition-based top-down target may be appropriate for specifying current sensor accuracy. This completes the lecture on the value of accuracy in my Battery Management Systems course. If you like what you saw, please help this course get seen. Share it with a colleague. Share it with a favorite college professor. Like, comment. Thanks.